go. Already up. Okay, let me find that screen then. There it is. All right, very good. So here we go. We're into lesson 3. We're going to talk about the relational model. We're going to talk about how we specify the data that we want to extract from a relational database. And we're going to express that in terms of something called a relational algebra, because this really helps you understand what the operations are that you do when you use a relational database. But before we do that, I want to do a little bit of a review here. Okay, so I have a picture here. And can anybody tell me what the relations are in this picture? Does anybody remember from last class? So the relations in this picture are essentially the two tables. You know, tables and relations, we kind of use the word somewhat synonymously. So the two relations in this picture are courses and instructors. Those are the two relations. Can anybody tell me what an instance of instructors would be? Yeah, Andrew. No, if you remember, the columns are not the instances. The instances are the values in any given tuple or row. Yeah, so the instance in this case for instructor would be 98345 Kim electrical engineering 80,000 would be one instance of the instructor's relation. Okay, who can tell me what the schema is for the instructor's relation? Anybody remember that? All right, well, the schema is the collection of attributes. The attributes are the columns, the collection of attributes that make up the instructor relations. So in this case, the schema for instructors is ID, name, department name, and salary. That's the schema for the instructor's relation. And don't worry if you don't remember this yet. You know, we'll be reviewing this in quite a bit of detail over the course of this discussion. All right, a tuple in the instructor relation is any single row. Each of these rows is a tuple in the relation. You know, consists of the instances of the schema. An instance of the schema within a row is a tuple. The attributes of the instructor relation are the ID. ID is an attribute of instructor. Name is an attribute of instructor. Department name and salary. Okay, the domain of an attribute is the set of allowable values that attribute can take. So in the case of ID, the domain of ID is a 5-digit number. In the case of name, the domain of the name is a set of characters of, let's say, no more than 30 characters. Yes. The domain is, if you guys think about programming, you know, when you declare your variables in programming, you declare those variables of being a certain type, and the type defines the allowable values for that variable. So, you know, the domain is essentially the type of the attributes, right? So character 20, you know, character 36, or numeric. Okay, a key or candidate key is any field in the relation that would uniquely identify a tuple in that relation. So a candidate key for instructors might be the ID, because the ID, there are no duplicate IDs. You know, every instructor has a unique ID. So since ID is a unique field within instructors, or a field with unique values, that is a candidate key for the instructor field. Is there any other candidate key field that you could see for instructors? The name, yeah, in this particular case, you know, the last name is unique. You know, so we can tell if somebody says, okay, I want the record corresponding to Katz, we know that that record is the fourth record in this table. So that is a candidate key. But the problem with using things like names as keys is, you know, we might wind up having a professor with the same name. So although it's a candidate key for this relation, you know, we would look at our candidate keys and we might decide, you know, ID is a better candidate key because that one we can be assured to maintain uniquely. Okay. So a candidate, you know, from a candidate key, we would pick a specific key. And a super key might contain that key, you know, but a super key is a candidate key that might include multiple fields. So, you know, we could use ID and name as a key into this, and that would be a super key of another key field, which would be the ID field. Okay, a foreign key. You'll notice that each course has to have an instructor. Okay, and the way we tell who the instructor is for this course is we have a numeric value here that corresponds to an instructor ID. So it points to this table of instructor information. That's what's called a foreign key. That's the thing that relates the course's relation to the instructor's relation. Okay. So the foreign key in this case is the instructor ID field in the course's relation. How are we doing with this so far? Okay, and when we have a relationship between two relations that's implemented by a foreign key and a what's called a primary key, the referencing relation is courses and the referenced relation is instructors. So you'll hear these terms as we discuss the relational model. So in this case, course and instructor are two relations. Course has one instance, and instructor has 12 instances. The schema for instructor consists of ID name, department name, and salary. And for course, it's course ID, course name, schedule, and instructor ID. Okay, so this slide helps a little bit with these definitions. And 222 Einstein physics 95,000 is the first tuple or row in instructor. Make sense to everybody so far? Any questions on this so far? All right, let's keep going. Name is an attribute of instructor. The domain for salary is positive numbers with up to 2 decimal places. Okay, I'll get into non-atomic or atomic and non-atomic domains in just a second. All right, so let's look at course in particular and look at the attributes of course. What are the attributes of course? Can somebody tell me? Yeah. Course name is one attribute of course. Yep. What are the other attributes? Course ID, schedule, and instructor ID. Yes. Okay. So if we look at those attributes of course, is there any one of those that you can see that we might break out into multiple attributes? Any of those that look like they might be broken up further? Yeah, Andrew. No, you're absolutely right. Schedule is the right answer. You'll notice that schedule has days in it. You'll notice that schedule has a start time and an end time. You know, if we want to ask certain questions about this course relation, we might want to break those things out to make those questions easier to ask. Like if we want to know every class that meets on a Tuesday, you know, it would probably make sense to have the day a separate attribute, right? If we want to know every class that starts at 11 a.m., we might want to break that out into a separate attribute. So, you know, the attribute that's not atomic here is schedule, because we might want to break that out further. We can choose to break that out further. Okay, so schedule in this case is a non-atomic attribute. Okay, the various super keys for instructor are ID and name. You know, these are candidate keys that we can use to uniquely identify each of the records or tuples in instructor. Okay. In this particular case, we're choosing ID as the primary key of this table because that we know uniquely identifies each tuple in the table. And we're referencing those records from course via the instructor ID, which is a foreign key in the course relation. And that's how we relate these tables, these relations to one another. They're related. And if you remember our entity relationship diagram, you know, that we did at the beginning, we said that an instructor teaches a course. You know, the way we know that that instructor teaches the course is because the instructor ID, the foreign key in course, points to that instructor. So course is the referencing relation, and instructor is the referenced relation. Everybody good with this so far? Makes sense? All right, and we'll be reviewing this stuff in more detail as we go along. Okay, now it's going to get a little bit tricky. But these are the relational algebra operators. These are the operations that you can perform on the relations in a relational database. The first one is select. And when you do a select, let me show you an example of this. If I say I want to select the instructor from the instructor relation whose last name is Mozart, okay, that is a select. I am selecting one tuple out of this relation. Okay, so a select operation allows you to specify a condition that matches some tuple or set of tuples in a relation and will reference that set of tuples. Okay, I could say, for example, select from instructor where department name equals computer science. Okay, which records would I get back for that? If I said select from instructor where department name equals computer science. Who are those instructors? Yeah, Zach. That's exactly right. So, you know, that's a select operation. When you do a select operation, you're specifying the relation, in this case, instructor, and you're specifying a condition or a predicate, in this case, where department name equals computer science. Okay, so I could write that expression with this symbol. This is I think it's a sigma. They use Greek letters. And I would say department name equals computer science. And in the parentheses, I'd put instructor because I'm referencing the instructor relation. Does that make sense to everybody? All right. Yes, exactly. Exactly. Okay, so that is one operation I can do on a relation. Another operation I can do is a project. So for this relation, for example, I could say project the department name for the relationship instructor, for the relation instructor. Okay? If I project department name for relation instructor, what I would get is I would get physics, finance, history, computer science, electrical engineering, biology, and music. Okay? What that means is I just want that attribute of that relation. Okay? So I'm restricting what I get back to only being those attributes that I'm concerned with. So the way we would specify that is using the symbol, the project symbol, and the list of attributes that we want, and we'd specify the relation. Okay? So those are the two most basic ones. And those generally operate on a single relation. Okay? We also have more complex ones. So we have set operations. When you think of a union of two sets, I don't know if you guys remember this. You know, I think you guys did sets in high school algebra and stuff like that. But if I have a set, oh, no marker here. Good thing I bring my own. Somewhere. There it is. I have a set A, B, C, and I have a set C, D, E. Notice that both of these sets have C in them. I did that on purpose. Okay. If I do a union of these sets, does anybody remember what the result of doing a union of these sets would be? Yeah. Yeah, it combines them. The result would be A, B, C, D, E. You know, it doesn't repeat elements that are in both sets. It just makes sure that the resulting set contains everything that is, listen to the word I'm about to use, in this set or in this set. Okay, anything that is in this set or in this set. So when you see this union thing, this U facing up, think of the word or. Okay. All right, now if I do A, B, C, my Bluetooth just dropped. Oh no, somebody just logged into it. Okay, if I do A, B, C, intersection CDE. Does anybody remember what that is? Yeah. Yeah, it's just C. That's exactly right. The answer is C. And the word that I want you to think of is that this is anything that is in here and in here. Okay? I don't know about you guys. I find that a little confusing because when you think of union, you think, but these are the words that go with those different things. Okay? So that's union and intersection. Union is or, and an intersection is and. Now, what if I do A, B, C difference? I better erase because, all right, I'll do it over here where you can see it. I do A, B, C difference D, C, D, E. Yeah. So in this case, order is important. It would be, yeah, it would be A, B, D, E. Yeah. Actually, so those are the things that are in one set and in the other set. Actually, in this case, I'm sorry. It would be AB. It would be AB. Order is important. It would only be AB. Now, if I did CDE minus ABC, in that case, it would be DE. Okay, so order is important for this. Yeah, you get rid of anything. What this means is anything that's in this set that's not in the second, anything that's in the first set that's not in the second set. So when you think about it, if I do a select and I get one set, and then I do a select and I get another set, I can then use these operations to reduce, to compare to operate on those two different sets. Okay, and we'll give some examples of that. Okay, so let me hold off on the other ones. I've got slides that address those specifically. Let's go through a little bit of a detailed example here. All right, so let's start with the select operation. So here we're selecting from the instructor relation where the department name equals physics. Okay, this is similar to the example that we did before. So here's the instructor relation. We find all the records that have department name equal to physics. And we find Einstein and we find Gold, and the resulting relation is there, Einstein and Gold. Okay, and the way that we write that is we write the select symbol, we write the predicate department name equals physics, and we write instructor as the relation. Okay. So that's an example of a select predicate. We can also use various other symbols, in our predicate. We can use equal, not equal, greater than or equal, less than or equal to. And we can also use ands, ors, and nots, logical operators. So in this particular case, there we go, we are selecting from the instructor relation where the department name equals physics and the salary is greater than 90,000. Okay, so in this case, we're putting together a complex predicate that is one condition and an and a second condition. Does that make sense? Any questions on that? Okay. And the other thing that we can do is we can use multiple fields in this expression, or multiple attributes. So for example, if we had building names, we could say we want to select those records from the department. If we had a relation that had department and the buildings that they were in, we would want to find those records where the department name was the same as the building name. So what kind of records would those return? That would return the case where, for example, the computer science department resides in the computer science building, versus those cases where the physics department resides in the John Larson physics building, or the John Larson building. Okay, so we can specify predicates that include multiple fields in the relation. Okay. So, once again, for the project operation, we list the attributes that we want. So, for example, if we do a project on ID, name, and salary for the instructor relation, it would give us just the ID, the name, and the salary. It would not give us the department name. Okay, so we list the records, or we list the attributes that we want, and we just get those attributes, and we don't get any other attributes other than the ones we list. Okay, so that's all well and good, but how do we do useful things with this? All right. There we go. So now what I want to do is I want to know what classes, what are the names of the classes, or what are the numbers of the classes, I should say, the class numbers. What are the class numbers taught by, or class names, we'll call them class names, CSIT, whatever. Class names taught by instructor two. Can anybody tell me how I might write an expression that would tell me this? So let me bring up the instructor. Let me bring up those relations again for you. Does anybody want to take a cut at answering that question in the form of a relational algebra statement? Okay. So the first thing I need to know is I need to know which classes are taught by instructor, or which records correspond to instructor 2222. Okay. So that's the first thing I need to know. So what I want to know is I want to do a select where instructor ID equals 2, 2, 2, 2, 2. And what relation am I looking at? I'm looking at course. That's the relation I'm looking at. Okay, but what do I want to know about those records where the instructor is 2, 2, 2, 2, 2? I only want to know the course name, right? That's all I want to know. So I want to take this and I just want the course name. Okay, so I'm doing a project on that select. Does that make sense to everybody? Does everybody understand that? It's a little complex, yeah. Because in the parentheses, we always have to identify what table or relation that data is coming from. But yeah, good question. So when we look at these algebras, we have to understand what the meaning is of the various piece parts of it. In this case, this is a relation. When we select from a relation, we produce another, essentially a temporary relation that we can then project the fields from that we need. Okay? So this would specify the answer to this question. Okay? So we've translated this question from an English statement, a statement in plain English, to essentially an algebra that specifies a design for the operation that will go against this database to retrieve that information. Okay. And the good thing about doing it in this is, this works regardless of what database you use it on. This is a statement of what end result you want. This is a mathematical way of representing what your end result is that you want. And you can hand this to a programmer and they can program it in whatever language they want, to retrieve that information. You can do this in SQL, obviously, and that's what we're going to be doing ultimately. But, I could hand this to somebody who's writing a Java program and say, this is what I want, write a program to do that. Okay. So this algebra gives you an implementation independent way of saying what result you want for a particular query or request. Okay. So let's try another one. Let me see if you guys can do this. So I would like to know the names of every instructor who makes less than $70,000. Who wants to try that one for me? These poor guys are underpaid. I want to find out who these underpaid guys are. Well, no, they're not underpaid. They're underpaid relative to their peers. But I want to find the names of all instructors who make less than $70,000. Yeah. I'll draw the first part for you. Hang on. Let me get you started here. Okay, there's the select symbol. Yep, salary less than 70,000. Good. For instructor. That's the first part of the statement. 100% right. Yeah, Zach. Bingo. Exactly right. Fantastic. All right, we're rolling now. Good stuff. That's a statement And in this case, we didn't have an equal sign. We had a less than sign here, but we've represented the predicate. We've selected based on that predicate, and we've projected based on the field that we wanted from that request. All right. So, things get a little bit more complex in just a moment. So I don't want to blow you out of the water yet, but you guys, you've got the basic, the basic statement, the single level statement, and now you've got a compound statement that you built based on these simpler operations. So that's great. All right, so let's move on. Yep. So composition of relational, there we go. All right, so here's another example. That's the name of everybody who's in the physics department. All right, Cartesian product. Now, this one's kind of funny because you never really use it, but it's necessary to understand the next one that you do use. So let me show you what a Cartesian product is. Yeah, so this is, yeah, so if I, let me go back to the original relations here. The Cartesian product of course and instructor would be, of instructor and course, let's do it that way, would be 222 Einstein Physics 95,000 CSIT213 database systems, Tuesday, Thursday, 45565. And then the next one with that, and then the next one with that. It's like every combination of these two tables is the Cartesian product of this table. So instructor, Cartesian product course would be every combination of the tuples in these two tables, which is, in my opinion, bloody well useless, right? Because that doesn't tell you which instructor teaches that course. That just tells you every possible option for which instructor, which instructor record would go with that course. The only one that's really meaningful, though, is the one where the instructor ID matches the ID. That's really the one we want, right? So Cartesian product gives you all combinations, which once again is bloody well useless. I've turned British all of a sudden. All right, but it's pretty much useless. So, we want a different operation other than the Cartesian operation to bring these tables together. But, the Cartesian operation is an operation that you might do in a database. And you can see that you've got combinations here that don't mean much. And buried in here, you got the combination, 151, 151, where that matches, where that person is actually teaching that class. Okay, that's the Cartesian operation. So I've taught it to you. You can promptly forget it. Not really. But that one you won't be using very much. But the one you will be using is called the join operation. And the join operation, one way to represent that is you select from the Cartesian operation only those records where those fields are equal, those ID fields are equal. Okay, so this is like a longhand way of writing a join operation. So if I'm selecting, things are getting worse with this marker. There we go. See if I can make this clearer on the board. So if I select the case where the instructor dot ID, that's how I say the ID field of the instructor relation, equals course dot instructor ID. And I select from instructor Cartesian product course, I get only those records where the ID matches. And that's really what I want, right? That tells me what instructor teaches what course. Right? Does everybody understand that? All right. But the good news is, rather than having to write this out in this longhand way, our relational algebra gives us a shorthand for doing that. Okay, here's the result of that operation, for the courses that they had here. They use somewhat different courses. But the way we write that in our relational algebra is, instead of using the Cartesian product symbol, we use this symbol. It's kind of like a figure 8 on its side with a flat top and bottom. It's, two lines where we're connecting the points in an X. And what we say is instructor course, and we have here instructor dot ID equals course dot instructor ID. Okay, and that's what's called a join. So once again, we've got one relation, relation 1, relation 2. These are the two relations we're joining. And this predicate says what fields, what conditions between those fields in those relations needs to be true in order to join them. Yes. Yeah. Yeah, well, they use teaches for course. Ours were called course and instructor. Okay. Okay. So that's the join operation. The join operation is really, along with select and project, is really the most fundamental operation in a relational database. I mean, that's the way we relate one table to another, is we join those tables together. And if you remember, we discussed in our earlier class that the reason we break these things up into tables in the first place is we don't want to repeat fields, we don't want to store them, but we do need to be able to put them back together again, right? We don't want to repeat storage. We don't want to store things more than is necessary, but we need some way to put them back together again. And the way we put them back together again is through the join operation. All right, so who's ready for a tough question here? You guys ready to think about something for a little bit? All right, here's my question for you. Here's a nice relational algebra problem. I'm going to put a word problem on the board again. And you guys are going to help me through the answer here. All right, the word problem here is what is the name and salary of the instructor who teaches CSIT 213. Okay? So, you're working for the HR department in Ocean County College. And you're looking at this instructor table and this course table. And you want to know what the salary is for the instructor who teaches instructors who teach course CSIT 213. Who wants to take a cut at that? Who wants to take a cut at what the first statement might be? Go ahead, Zach. Okay, so we do need to select in this. We do need to select in this because we need to find a record that corresponds to CSIT 213. So there is a select in this. What other operation might we have in the statement? Yeah. Yeah, so we need a select in here. And we also need a join in here because we need to be able to pull the instructor data together with the course data. So there's a join in here also. And remember, we just want the name and the salary. We don't want all this other information that comes out of this. Yeah. Yeah, so we need a project also. All right, so we need these three operations, but how do we decide what to do first? Okay. Yeah. So let me say this. Who remembers when we were talking about query processing? We were talking about the parts of a database system, and we said that the query processor includes query optimization. So, we don't worry so much about limiting the set that we return, but that was a good answer actually, because if you're thinking about, how to do this in real life, you want to get your set smaller before you join it with bigger things. So that's a really good answer. But for the purpose of this relational algebra, we're not going to be concerned about optimizing this. We just want to make sure that we get the statement correct on what we need. But I'll come back to your answer for SQL, because when we do SQL, that'll be important. What you just said will be very important. All right. So what I'm going to tell you right now is a very important process that you guys are going to have to remember. This is going to be, remember the expression, this is going to be on the test. This is going to be on the test. Okay. So what I'm about to teach you is how to put together these relational algebra expressions in a way that's organized so that you can do it, and remember how to do it. So my advice to you is when you get a question like this, what is the name and salary of the instructor who teaches CSIT 213? Step one is figure out what relations or tables you need. Okay, that's step one. And in this case, what relations or tables do we need? We need instructor, and we need course, right? So let me go back to that screen so we can see it. We need instructor and we need course. So that's step number one, is figure out what tables you need. Step number two is join those tables together. Okay? So the first part of our relational algebra statement will be instructor, join, course. And of course, we have to specify on what fields we join them. So we're going to join them on instructor ID equals course instructor ID, right? So that's step one. Okay, the next thing we're going to have to do is we want to find the records that come out of this that are the records that we're interested in. Okay, so the next thing we're going to do is we're going to do a select. And in this case, what records are we interested in? Those, what's the predicate here for this select? Can anybody tell me? Exactly, course ID, exactly right. Course ID equals CS, course ID. And we could say course ID, but since there's only one course ID here, we don't have to do that. But that's exactly right. Course ID equals CSIT213. That in quotes, because that's, that's a field value rather than a field name. All right, and the last thing we need to figure out is what fields we need of this, right? So we're going to project this whole thing. And what fields do we need? Name and salary, exactly. So this would be name, comma, salary. And that's your relational algebra expression for that question. Okay? How are we doing with this? Does that make sense to everybody? So, this whole process, like I said, first figure out what tables you need. And by the way, there might be complex relationships where you have a table in the middle here. And you might just need to join that table in so that you know how to relate this other table, but you might not even use anything from that table, right? So, but you have to know that you'll need that table. And I'll give some examples of that as we get more complex in this stuff. But the first thing you do is figure out what tables you need. Join them together, select the right records, and then project the fields that you need. Now, per the point that was made earlier, if we were doing this to optimize, we'd probably want to select, a fewer number of records before we join them, because that would reduce our interim set. That's probably a good thing to do. And we could certainly write this expression that way. But, for the purpose of the relational algebra, we don't need to worry about that. When we actually get into implementing the relational algebra, then we need to worry about it. That's more of an implementation rather than a design issue. This just says what we want to get back. Okay? How are we doing with that? Okay. So now here's a tough one. You thought that one was hard. If you thought that one was hard, this one's even harder. Let me erase the board again. All right, welcome to math class. Okay, so this next one is I want to find the instructors. Let me figure out a good one here. Let's do instructors. I want to do this two ways. How about that? Let's do this problem two ways. I want to find all instructors in the computer science department who make more than $90,000 a year. Okay, who can give me one way to write that expression? All instructors in the computer science department who make more than $90,000 a year. So one way we can write it, we're doing a select on the instructor relation. And the department name is equal to computer science. But we also want and salary is greater than $90,000 a year. Oop, 90,000. There we go. That's one way I can write it. Anybody want to cut it a different way to write that? So this symbol means and, if you remember from the other view graph. Where department name equals computer science. From instructor. But I'm going to take the intersection of that with the set of instructors whose salary is greater than $90,000. So that's two sets. I'm taking the intersection of those two sets, and I get the same result as in the first statement. Okay. Does everybody understand those two statements as equivalent? Does that make sense? I shouldn't ask. Are there any questions on that? All right. All right, so that's how you use this algebra to translate these questions, these human questions, into something that can be implemented in a database implementation. Okay, and you can do the same with union operators, and we did set intersection there. All right, set difference. Let's look at set difference. So, in order to do unions and differences, I should mention, whatever results from the left side of the intersection or union, you have to have the same fields on both sides. You can't have things with different fields. You can't have things that return different attributes and have a union or an intersection of them. All right. So, the example, let me look at some of these. Let's go through some of these examples. Let's start with the union. All right. So this example asks for all courses that are taught in the fall semester and in the spring semester, both, or in both. So it's either in the fall or in the spring, right? We remember the word or for union. That's why this is a union. So first we're going to find the course IDs of those courses that are taught in the fall of 2017. And we're going to take the or of that, or the union of that, with those courses that are taught in the spring of 2018. So this will give us the set of courses that are either taught in fall 2017 or are taught in spring of 2018, or both. Okay? So that's a union. And the important thing there, once again, is that both of those expressions that are part of the union have to return exactly the same fields. They can't return different fields. Okay, similarly, okay, so, this would be the result for their sample data that they use in the book. Okay, similarly, if we wanted those courses that are taught in both, only those courses that are taught in both spring 2017 fall 2017 and spring 2018, we would take the intersection, because that means it's taught in the one and in the other, right? If we want the ones that are taught in one and not in the other, then we take the difference. So the things that are taught in fall 2017 that are not taught in spring 2018 would be the set difference. Does that make sense? So that's how the set operations work. Okay. Now we can name these things. You know, we can produce a select operation, and we'll name this one physics. We want to select from instructor where the department name equals physics, and we'll name that the physics, that new result, the physics result. Okay, and if we select where the department name equals music, we can name that the music result. And the way we represent that is with this arrow. You know, that's kind of an assignment thing, like you do in programming. And then we can do a further operation on those two things. We can do physics union music to find out which instructors teach either physics or music. Okay, so that's the assignment operation. And the rename operation allows us to rename the fields that are returned from a particular expression to give them new names. So, you know, in this example, for example, we have course ID, we had instructor ID and ID, and those were, you know, if those were returned by the same query, we would have to rename one of those so that they wouldn't be confused. So we have a rename operation where if this expression returns a set of attributes, if we use the rename operation, it will rename those attributes, whatever we list here. So let's see an example of that. Oh, no, we don't have an example of that. All right, I'll give an example of that. Let me show you the rename operation. So I'm going to join instructor. I'm going to join that with course, where instructor ID equals course instructor.id equals course instructor ID. I'm going to project just the instructor name and the course number. And I'm going to rename the result of this. We'll call this, all right, we'll assign this to teaches. You know, this is assigned to teaches. And what I'm going to do is I'm going to rename what's in the teaches relation, or teaches expression, professor and course. Okay, so what comes out of this is the name of an instructor and a course number. And instead of calling it name and course number, I'm going to call it professor and course. Okay, so the table, the relation that comes out of this would have the columns professor and course, And it would have a list of professors and the courses that they teach. Does that make sense? You good with that one? All right, we did these equivalent queries already. You know, you can do ands, or you can do selects of selects, you know, or you can do intersections, you know, all of these expressions that you see on this particular slide all yield the same result. So there are several ways that you can write the same thing. Okay, and you know, per the point that was made earlier, you know, we could have done the select before the join or the join before the select. You know, the method that I taught you is a good organized way of doing it, but you could have written it this way as well, as was suggested by Andrew in the back there earlier. Okay. So I'm going to hold off on this one until the next class. Let me stop here for the time being. All right. So that's the relational algebra. And we're going to have an assignment on that following your next assignment. You know, for your next assignment, I'm going to ask you to just think of some tables that would be part of a Netflix database. So I'm asking you for 3 tables that would be part of the Netflix database, or 3 relations that would be used by Netflix. That's your next assignment. That's due, I guess, a week from today. And then following that, we're going to have I've got a relational algebra assignment for you to do. But before we do that assignment, I want to go through a few more examples in class. We're going to do some exercises in class to get more familiar with this relational algebra. So that's what's coming up. All right, so just as a reminder, what happened to my display? Bear with me a second. Let me reshare this. All right, so just as a reminder, hang on. There we go. Hopefully by the end of today, either using your own computer or the computers in the library, or getting the VMware stuff working, you will have completed just running that simple query in SQL Server. You know, like I said, I want to make sure that you guys are ready to run that when the time comes. So I wanted to make sure that you know how to do that. So that's the first assignment. That's due end of today. By a week from today, you're going to give me 3 tables for Netflix. You know, you're going to describe 3 relations. And don't forget to include the various elements that we went over today. You know, what are your keys? What are your foreign keys? All that good stuff. You know, please make sure to include those in your table. Refer to the earliest slides that we did today when you put those tables together to make sure that you are relating the things that you're representing for Netflix. So that's your assignment for a week from today. And between now and next week, we're going to do some more with the relational algebra. And then you guys are going to have an assignment to do some of these relational algebra statements. But we're going to get to practice that a little bit more in the next couple of classes before we. Okay, so that's all I had for today. Does anybody have any questions or comments? Stuff starting to make sense? All right. If not, I'll let you all go, and I'll wish you a great rest of your day. And we'll see you all on Thursday. Thank you, Andrew.